Okay, welcome students to this lecture. We are going to study about Taylor and Maclaurin series. So as from the preceding exercises or what we've been solving, we have been trying to find the power series of functions in some restricted domains. So here we consider for a general case. So in the preceding, section, we were able to find power series representation for certain restricted class of functions. So here we investigate more general problem. So which function have power series so which functions have power series representations? And another question that we want to answer is how can we find such representations? So these are the big problem that we need to answer. So we start by supposing that f is any function that can be represented by a power series. So let's call it let's call it equation 1. So f of x equals to c naught plus c1 x minus a plus c2 x minus a square plus c3 x minus a power 3, where x minus a is less than r. And then, and let to determine what the coefficients Cn must be in terms of f. So to begin with, notice that if we put x equals to a in equation 1, then all the terms after the first one are 0, and we get f of a equals to c naught. And then if we apply now, we have f prime of x is given by c1 plus 2 c2x minus a plus 3c3 x minus a square plus 4c4 x minus a power 3 plus several terms for x minus a less than r. So let's call this one equation 2. Substitute x equals to a in 2 gives the substitution of x equals to a in 2 gives f prime of a equals to c1. Let's get the second derivative. Second derivative of x will be given by, we differentiate now 2. This one will be equation 3. Will be 2c2 plus 2 times 3 c3 into x minus a plus 3 times 4 c4 into x minus a square x minus a is still less than r, and also again substitute x equals to a in equation 3. We get f double prime of x will be given by this f double prime of a. Will be given by 2c2. So also differentiate equation 3. So we'll get f double prime of triple prime of x will be 2 times 3 c3 plus 2 times 3 times 4 c4 into x minus a power 1 plus 3 times 4 times 5 c5 x minus a power 2 plus other several terms with x minus a less than r, and again replace x equals to a in 4. So we'll have, this will be given by 2 times 3 c3 which will be 3 factorial C3. Now this pattern continues. So by now you can see the pattern, i.e. if we are to get the fourth derivative at A, we should get 2 by 3 by 4C4, which is the same as 4 factorial C4. And in general, nth derivative at A will be given by 2 by 3 by 4 up to n times Cn, which will be n factorial times Cn. So solving this equation for the nth coefficient, we get Cn equals to the nth derivative of A over n factorial. So this formula remains valid even for n equals to 0 if we adopt the convention that 0 factorial equals to 1 and 0th derivative of a function is the function itself. So thus we have proved the following theorem. Theorem if f has a power series representation or expansion at A, that is, if f of x equals to summation n from 0 to infinity Cn x minus a power n for x minus a less than r, then its coefficient are given by the formula Cn equals to the nth derivative of a over n factorial. Now we say, substituting this formula for Cn back into the series, we see that if f has a power series expansion at A, then it must be of the following. Form, that f of x equals to summation n from 0 to infinity f derivative at A over n factorial x minus a power n. So which is the same as f at A plus f prime at A over 1 factorial x minus a plus f double prime over 2 factorial x minus a square plus the triple derivative at A over 3 factorial x minus a3 factorial plus several terms. Nth derivative at A over n factorial x minus a power n plus other terms so let's call this one equation 6. So this equation 6, this is called the Taylor's series of the function f at A or about A or centered at A. For special cases, for the special case A equals to 0, the Taylor series becomes f of x summation n 0 to infinity nth derivative at 0 over n factorial x power n, which is f at 0 plus f prime at 0 over 1 factorial at 0 over 2 factorial at 0 over 3 factorial x cubed plus so this one here call it 7 is called, this case is called Maclaurin's series. So say NB, we have shown that if F can be represented as a power series about A such that such functions are called analytic functions at A. Then F is equal its Taylor series. So, quick example. Find the Maclaurin series of the function f of x equals to e raised power x, and find its radius of convergence. So solution, this is a very easy exercise to work out. So f of x is given by e raised power x. F is given by e raised power x, so that fn at 0 is e raised power 0 equals to 1 for all n. So therefore, the Taylor series for f at 0, i.e. the Maclaurin series, is summation n from 0 to infinity nth derivative at 0 over n factorial x power n is summation n0 to infinity x power n over n factorial, which is 1 plus x over 1 factorial plus x squared over 2 factorial plus x cubed over 3 factorial plus x power 4 over 4 factorial plus x power n over n factorial plus other terms. Now, to find the radius of convergence, we let an to be x power n over n factorial, which means an plus 1 will be x n plus 1 over n plus 1 factorial. So limit as n approaches infinity of an will be limit as n approaches infinity of xn plus 1 over n plus 1 factorial times n factorial over x power n, which will be limit as n approaches infinity of x power n times x power 1 times n factorial over n plus 1 n factorial times x power n. Clearly, this and this cancels out, this and this cancels out. So we'll have limit as n approaches infinity of x over n plus 1, which is nothing but x limit as n approaches infinity of 1 over n plus 1, which is actually 0 because this limit approaches 0. And this is less than 1. So by the ratio test, the series converges for all x and the radius of convergence is r, which is infinity. From then, definition, really not a definition but a theorem. If f of x equals to t n of x plus r n of x, where Tn of x is the nth degree Taylor polynomial of f about a and limit as n approaches infinity of r n of x equals to 0 for x minus a less than r, then f is equal to the sum of its Taylor series on the interval x minus a less than r, i.e. f is analytic at a. And then there's what we call Taylor's formula. So Taylor's formula, if f has n plus 1 derivatives, in an interval I that contains the number A then for all x in I, there is a number z strictly between x and A such that the remainder term in the Taylor series can be expressed as Rn of x equals to nth plus 1 derivative at z over n plus 1 factorial x minus a power n plus 1. NB one n equals to 0 if we put x equals to b and z equals to c in Taylor's formula, we get f of b equals to f of a plus f prime of c into b minus a which is the mean value theorem and then note number 2, notice that the remainder term Rn of x equals to n plus 1 over n plus 1 factorial x minus a power n plus 1 is very similar to the terms in the Taylor series except that is evaluated at z instead of at a. all we can say is that the number z lies somewhere between x and a. The expression for Rn of x is known as the Lagrange form of the remainder term. Lagrange's form of the remainder term. So that's what we have. So do as many examples as possible on the Taylor and Maclaurin series. To be able to solve some questions on the same. So it's an exercise. Find the Maclaurin series for A, f of x equals to sin x, B, f of x equals to cos x. So have a good day.